What's up, guys? So, welcome to the next part of your chemistry periodic table. So, today we are going to look into the group 17 elements, which are the halogens. All right. So, for the halogens, basically you have five elements: fluorine, chlorine, bromine, iodine, and astatine. Okay, so technically for your level form 4, you will only be learning more about fluorine until iodine, right? Astatine, you only need to know the physical state, which is that astatine, they actually exist as solids. Okay, alright, so group 17 elements. Okay, later you just fill in the bubble map. Okay, electron arrangement. Alright, so I believe that you know how to write the electron arrangement, but I'm just going to show you for bromine. Okay, all right, so for bromine, the electron arrangement, since my proton number is 35, so this one is more than 20. So when it's more than 20, remember that your third shell can either be 8 or 18 electrons. So in this case, for bromine, right, okay, 2 8, all right, third shell, this one will be 18 instead of 8. Okay, so 2, 8, 18, 7. So total should be 35. Alright, so number of shells 4, meaning that bromine is located in period 4. So let's check 1, 2, 3, 4, period 4, and then there it is. Okay, bromine. Alright, so for iodine, it will be the same case, just that iodine is in period 5. Oh, excuse me. So if I have 5 shells, alright, 5 shells, okay, so later when you try and write out the electron arrangement, please check and see whether the third and fourth shell should be 18 or 8 electrons. Okay, so I believe should be no problem there. Alright, so let's look into the physical properties of the group 17. Alright, so technically group 17 elements, the first thing that you need to know is that of course they are non-metals because they are in the right side of the periodic table. All right, and then another thing is that they do not exist naturally, meaning that you won't be able to find, for example, chlorine gas or bromine liquid in nature, meaning you don't dig the ground and then suddenly you will see bromine liquid coming up. No, that's impossible. All right, so technically for group 17 elements, they only exist as what they call metal halides or in mineral forms. And one of the most famous mineral form that you can see at your home that you eat every day is the sodium chloride. Okay, so technically for halogens, right, they exist as minerals or metal halides. Okay, sodium chloride, potassium iodide, so on and so forth. Okay, and then do not conduct heat. All right, okay, they do not conduct heat, they do not conduct electricity, and then they have low melting and low boiling point. Okay, so if you look at the slide on the right side here, you will notice that unlike group 1 elements, okay, group 1 elements, their physical properties, or what we say, their appearance is actually almost the same. All are gray colors. But for group 17 elements, they have different colors for different elements. So this is very important for your exam. You must know the color of the elements. Alright. So first one, fluorine is pale yellow in color. Okay. Chlorine is yellow greenish. Where is the H? Okay, H is here. Right, yellow greenish. All right, bromine is brownish. Oh, H missing again. All right, iodine is purple solid. Okay, and then astatine, like I mentioned just now, it is solid but white in color. Okay, so it's important that you know the colors of the um, group 17 elements. All right, I can show you an example here. Okay, so for example, like this. Okay, in this case, the first one right here is the chlorine gas. Okay, it's actually slightly yellowish greenish color. All right, and then bromine, they exist as liquid. Okay, so it's brownish. Okay, and then this is iodine. It's purple in color. All right, so it's important that you know the colors of the elements. Okay, all right, boiling point. Okay, low melting and boiling point. If we say that they have low melting and boiling points, meaning they are okay, low melting and boiling point, meaning that they are very volatile. Okay, meaning they evaporate very easily. All right. So in many cases, especially when you store chemicals involving halogens, you cannot put it under the sun. You cannot put in where there are lights. Okay, it has to be in the dark cupboard or cabinet. Okay, that is why for halogens you cannot put it under the sun or any light sources because they are very volatile. If the temperature goes up, they evaporate very easily, and if they evaporate, it's actually very dangerous, especially to us humans. If you breathe in the vapors, right, basically you'll be getting you will it's actually toxic for us. Okay, so remember, halogens must be stored in cool, dark conditions. All right. Okay. So this one, high electronegativity. Okay. So I'm going to take some time to explain the meaning of electronegativity. This term, electronegativity, okay, is given when an element accepts an electron. Okay. Now, if you remember in your group 1, okay, so for group 1, all right, if you remember, they release electrons, right? All right, so basically group 1, they release electrons to form positive ions. Okay, so they form positive ions. Okay, so if you form positive ion or if you release electrons to form positive ion, the term given here is electropositive. Okay, whereas for group 17, all right, so since they are at the end of the periodic table, so technically they are going to accept electrons. Okay, so to release or accept will depend on the octet stability rule. All right, so elements on the left of the periodic table, group 1 and group 2, they will release electrons to achieve octet stability, whereas group 16, 17, 15 until 17, they will accept electron to achieve octet stability. All right, so since I accept electrons, I am going to form negative ions. Hence, the term given is electronegative. Okay, so another way that I can put it is that the electro here means that you love to become positive or you love to become negative. Right, so if we say an element is electropositive, meaning they love positive so much that they are going to form positive ions. So how do they form positive ions? Is by releasing electrons. Whereas any element that loves to become negative, they are going to form negative ions and they are going to accept electrons. Okay, so that is the meaning of the term electronegative. All right, basically the strength to attract the electrons. Okay, let me show you the proper definition here. Okay, if you see the definition here, strength of atom to pull electron towards its nucleus. All right, so later I'm just going to show you a few examples. Okay, so technically that is the meaning of electronegativity. All right, so the physical changes for group 17 elements. Okay, all right, so let's look at the physical properties right here. Okay, oops, let me just fix this. All right, atomic size. Okay, remember in your periodic table, as you go down, number of shell increases. Therefore, your atomic size is always increasing. Okay, because number of shells increases. Okay, doesn't matter which group. As you go down the group, size definitely will increase. All right, and then remember your melting and boiling points will also increase. Okay, why increase? First point is because size increases. So as the size becomes bigger, distance between molecules becomes shorter. Therefore, van der Waals forces is stronger. Okay, so remember that your melting and boiling point is depending on the van der Waals forces, and van der Waals forces are the attractive force between molecules. So the nearer the molecules, the stronger the force, meaning that you're going to need more heat energy. Alright, so more heat energy is needed to overcome the forces. Hence, melting and boiling point increases as you go down the group. Okay, now physical properties of fluorine and fluorine until iodine. Alright, now this one is very important. You must know the physical properties or the physical changes. Okay, so fluorine and chlorine, they exist as gas. Okay, bromine is liquid. Alright, and then iodine is solid. Okay, so two things here that you need to remember. One is the color of the element. Second is the state of the element. So technically the element, they are changing from top to bottom. It's gas, liquid, and then solid. Alright, so astatine also exists as solid since it's below iodine. Okay, now density of mass also of course will increase since mass increases down going down the group. Alright, so the color is very important, like I mentioned just now. Okay, so technically as you go down the group, the color will become darker and darker. So from fluorine, a pale yellow color, slowly it will change to a very dark color, which is iodine, which is purple in color. Alright, so the color of elements as you go down the group becomes darker. Okay, so fluorine is pale yellow. Okay, chlorine is yellow greenish. Alright, I hope I can spell greenish correctly. Okay, bromine is actually brown. Alright, whereas iodine is purple. Okay, so you need to remember the colors of the halogens. Very, very important. Right? So, without further ado, now let us go into the chemical properties. Alright, so that is it for the physical properties. Important is the color and also the physical state. Okay, so chemical properties. Alright, remember if you have similar chemical properties, it's because you have a similar valence electron. Okay, remember, if you have same valence electron, meaning you will have the same chemical properties. So in the case of the halogens, they have 7 valence electron. Okay, so remember group 17, meaning you have 7 valence electron, and they achieve stable octet by accepting 1 electron to form negatively charged ions. Okay, so this one, fluorine atom receives 1 electron to form stable. Oh, sorry, there's a mistake here. It's not a duplet. Alright, they form stable octet. Okay, alright, so let us draw out the electron arrangement so that you can see this. Okay, fluorine is 2, 7. Alright, so 2, 1, 2, 3, 4, 5, 6, 7. Okay, and then outermost shell, 7 valence electron. You only need 1 more to achieve octet stability, which is maximum of 8 electrons. Okay, so what they are going to do is that they are going to accept 1 electron. Alright, so after they accept 1 electron, then they will achieve the octet stability. Okay, so 2, 4, 6, 7, become ion, we must draw the bracket and we must write the charge. Except how many electrons, that will be my charge. So this is F negative. Alright, so fluorine atom receives 1 electron to form fluoride ion. Okay, so let's look at chlorine. So chlorine, alright, so chlorine, so 2, chlorine is 17, 2, 8, and then 1, 2, 3, 4, 5, 6, 7. Alright, and then they are going to accept 1 electron. Two. Okay, draw this faster. Cross. 6. Okay. 7. Alright. So this one is called, oh sorry, I will draw the bracket. Okay, draw bracket. Oh, now so we draw bracket. Then the charge, negative. Alright, so this one is called, oops, my spelling, oh my god. Okay, chloride ions. Okay, so technically, group 17 elements, they are going to form negative ions because electronegative. Okay, they are electronegative elements. Okay, love negative, right? Okay, so they will be accepting 1 electron to achieve stable octet. All right. So next, we are going to look at the reactivity. Okay, now for the reactivity of halogens, all right, it's important that you know it's going to be opposite with the group 1 called element. Okay, because as you go down the group, it will be slightly different. Alright, so in this case, alright, so for reactivity, in the case of group 1 elements, okay, and then this one will be group 17. Alright, so for reactivity, now if you remember that for group 1, as you go down the group, their reactivity increases. Okay, reactivity increases as you go down the group. So let's say this one is lithium, this one is sodium. Alright. So group 1 elements reactivity depends on how easy it is for the element to release electrons. Okay. So this one is release electron. Okay. The easier for you to release the electrons, the more reactive you are. So it depends on where is the valence electron. Alright, so in this case here the valence electron is nearer to the nucleus. So the force of the attractive force here is slightly stronger. So slightly more difficult to release the electron here. Whereas in the case of sodium, alright, the valence electron is further away from the nucleus. So it's easier to release the electrons. Therefore, reactivity will increase down the group. Okay, so for group 17 elements, their reactivity is going to be totally opposite from the group 1. Okay, so an easy way for you to remember is like this. Group 1, release electron, meaning as you go down the group, reactivity increases, right? So group 17 is totally opposite. Everything is opposite. Okay, so group 17 elements, as you go down to group, alright, what happens is that because this one is their reactivity is depending on how easy it is to accept electrons. So in this case, their reactivity will decrease. Alright, so the difference between the two what we call groups, okay, okay, decrease, because this one is accept, okay, accept electrons. It depends on how easy I can they call attract the electrons to come in. So let's say in the case of what they call fluorine, all right, so I only draw the valence electron, yeah, okay, so in this case I need one more to achieve octet stability. So maybe there's one more electron what do you call outside here, okay, one electron here moving, okay, so it will depend on how strong is the attractive force. So the nearer or the smaller the size, the stronger the attractive force of the nucleus, so that it's easier for them to pull the electrons to come in, okay. So as the shell increases, remember, as shell increases, distance is getting further from the nucleus, and then electron outside here, let's say for example, okay, let's say this one is chlorine, alright, so the valence electron here is 7, okay, I need one more to achieve octet stability. However, because here the nucleus is further away, alright, so it is slightly more difficult to pull the electrons to come in. Therefore, for group 17 elements going down the group, the reactivity will decrease because it's more difficult to pull the electrons to come in because you have more shells. More shells meaning you have more protective layers, so more difficult for the nucleus to attract the electrons. Okay, so these are the two differences between the group 1 and group 17 elements. Okay, so you need to be able to explain why group 1 elements reactivity increases and why group 17 elements the reactivity decreases, right? So let's look at the notes here. Okay, so they have 7 valence electron and then they achieve octet by accepting 1 electron to form negatively charged ion. Okay, so it depends on the tendency of the atom, okay, to receive electron. Alright, so as you go down group 17, okay, number of shell increases, atomic size increases. Okay, so atomic size increases, so outer shell becomes further away from the nucleus. Okay, so the strength of attraction, okay, the strength of attraction from proton in the nucleus to attract 1 electron into the outermost occupied shell becomes weaker. Okay, because you have more protective layer, alright, or more shells, so it's more difficult for the nucleus to attract the or to pull the electrons in. Okay, so the strength of a halogen atom to attract electron decreases from fluorine to astatine. Alright, therefore their reactivity decreases going down group 17. Okay, so remember the difference between group 17 and group 1, yeah? Alright, okay, next one. Okay, why they exist as diatomic molecule, meaning that for halogens, okay, they do not exist as a single atom, meaning you will not see them exist as this 1F atom, no. Alright, all halogens will exist as diatomic, meaning it will be F2, Cl2, I2, Br2. Okay, they do not exist as monoatomic, they exist as diatomic. Alright, so why do they exist as diatomic? Is because now if you see this is one atom of fluorine, okay, it is not stable for them to exist in this form, meaning if in what they call fluorine atom is actually not stable. Okay, to be stable, to be a stable compound, they need to actually follow the octet stability, right? Meaning if possible they would like to achieve octet stability. So for fluorine, chlorine, bromine, and iodine, we know that they need one more to achieve octet stability. So what they are going to do is that two friends here are going to share their electrons. Okay, they cannot donate. If donate, meaning they don't have enough to achieve octet. So the only way that they can achieve octet is by sharing their electrons. Okay, So two fluorine atoms will share their electrons, meaning each will share one electron, and then alright, so each will share electrons. So what happens is that, oops, let me just move this. Okay, so they are going to share their electrons. They are going to share their electrons. So fluorine 2, 4, 6, and then 8. Alright, I'm going to use another color to show the different atoms. Okay, so 2, 2, 3, 4, 5, 6, 7, 8. Okay, so technically that is how they can achieve octet stability. And that is why all what they call group 17 elements will exist as diatomic molecules. Okay, so that is the front part of the reaction. Alright, finally we are going to go into the chemical reactions of group 17. Similar to group 1, group 17 elements, you will also have 3 different chemical reactions. Okay, we are going to react with water, alkali, and also with iron. Okay, so this one is the what you call experimental setup. You need to be able to draw the experimental setup. All right, it's important that you know the diagram. Okay, before that, okay, the first part here. If you see here, you have these two things. Oops, just move this. All right, if you see, you have these two things right here: potassium manganate crystals and also concentrated hydrochloric acid. So basically, this one, the function here, okay, these two is actually to produce chlorine. Alright, because I already mentioned that they do not exist naturally. So if I want to have chlorine gas, I need to use a chemical reaction to produce the chlorine gas. So the two substances that you use to produce chlorine gas are these two. Alright, potassium manganate crystals and concentrated hydrochloric acid. If you mix these two things, they are going to produce the chlorine gas. Okay, alright, so liquid bromine and then solid iodine. Okay, so this is the reaction with water. Okay, so when an halogen reacts with water, they are going to produce the acid, and also another one is what we call the hydrochlorous, or the what they call hydrochlorous hydrobromous, and also hypobromous, sorry, hydrochlorous hypobromous, and also hypoiodous acid. Okay, so this one is the general formula. All right, so chlorine react with water to produce the acid and also the hypo or hydrochlorous acid. All right, so remember, we need to know the observation. Okay, so chlorine dissolves. Okay, remember, reactivity decreases, meaning you are going to dissolve fast and then slow as you go down the group. All right, so chlorine dissolves rapidly, okay, in water to form light yellow precipitate. Remember, you need to know the color of the precipitate. And since you are forming an acid, meaning you are going to change a blue litmus to red. Alright, and another very important thing is this: quickly decolorize. Okay, this one is very important. This is a very what they call special characteristics of halogen. After they change the litmus paper to red, it will decolorize. So I'm going to show you an example right here, the bleaching properties of chlorine. Okay, so technically this video right here, he is mixing the hydrochloric acid with the potassium manganate solution. Okay, so after he mix, he is going to produce the chlorine gas. Okay, so as you can see, they are producing the hydrochloric acid. That is why, if you notice, right? Okay, so if you see the red part here, this one is because of the hydrochloric acid. And then, if you notice the white part here at the bottom right here, alright, this one is because of the chlorine gas. Okay, they are going to decolorize the litmus paper. So this is a special properties for halogen. okay, after they change the litmus paper to red color, it's going to decolorize, meaning the color will disappear. Whereas for other types of acid, they will only change to red and the color will remain as red. Okay, the pink or the purple color here is because of the potassium manganate solution. Okay, so that is the meaning of decolorize. All right, so the balance equation, you can just refer to the slide right here, okay, on the right side, okay, or you can just refer to the general equation right here on the top. Okay, so remember to put the reversible arrow. Okay, and then for bromine, so this one is rapidly. So this one, we can say bromine dissolves, what we call slowly, okay, to form a brown solution. Okay, remember all the colors of the solution. It's going to be important. All right. Okay, and then changes blue to red and quickly decolorize. Okay, so the balance equation is this one. Okay, you're going to get the hydrobromic acid, HBr, and the hypobromous acid, HOBr. Okay, for iodine, you're going to dissolve very slowly because less reactive. Okay, and then you're going to form brown solution also. So it's important, both will get brown solution. Okay, just that this one will react faster, this one will react slower. Okay, and then for iodine, because it is less reactive, so the litmus paper is not decolorized. Okay, so you need to understand that for iodine, okay, litmus paper is not decolorized. Okay, whereas for chlorine and bromine, they will decolorize because they are more reactive compared to iodine. Okay, so your inference here, technically what we can conclude is that all three halogens will form acidic solution. Okay, so this is the first chemical reaction for halogens. Okay, the reaction with water. All right. Now the second is the reaction with alkali, sodium hydroxide or potassium hydroxide. It doesn't matter. Okay, so this is the general equation. Technically, you're going to get the metal halide and also the chloride or the bromine or iodide form. Okay, NaOCl, NaOBr, or NaOI. Okay, depending on which halogen is used. Okay, so your observation here, okay, for chlorine, so reactivity decreases, so it's the same thing actually. All right, greenish chlorine gas dissolves rapidly, okay, to form salt solution, or what we call neutral solution. Okay, to form neutral solution. Okay, neutral because you are getting salts. Okay, all these are salts. Sodium chloride, sodium chloride, and water. Okay, so the balance equation is based on this one. Okay, you will get sodium chloride, sodium chlorate. Okay, the bracket here is referring to the charge of the chlorate, the OCl. All right, and then make sure you need to balance off. Okay, 2 sodium, that's why we put 2 here. Okay, so our inference, okay, chlorine gas reacts what with sodium hydroxide to produce. Okay, so basically it's the same thing. All right, reacts rapidly, okay, to produce this one. Okay, and then for bromine and iodine, the reactivity decreases. So this one will dissolve slowly, this one will dissolve very slowly. Okay, and then for the inference, it will also be the same thing. All right, so I'm just going to show you the what we call chemical reactions or the equation for bromine and also iodine. Okay, so you will get sodium bromide, sodium bromate, and water. For iodine, you're going to get sodium iodide, sodium iodide. Okay, it's important that you remember the what they call product of the reaction. Okay, they will ask you to write the balanced chemical equation. Okay, so that is the reaction with what they call alkali. Okay, the final reaction of halogens is with iron. Okay, so this one is very important. technically what you're going to get is the iron chloride or the iron halide. Okay, so for this one, FeX3, this one can also be called as iron halide. So depending on what type of halogens you are using, okay, it will be iron chloride, iron bromide, or iron iodide. Okay, so the iron here will be 3 plus. Okay, remember, since it's 3 plus, that's why if you do the what they call chemical formula, E is 3 plus. Okay, and all halogens is minus. So cross, that's why you will get FeCl3. Okay, right here. Alright, so observation. So let us look at an example of the reaction between the halogens and iron wool. Okay, so we are going to look at the reaction of halogens with iron. Alright, so technically we need to burn the iron, and then we are going to put it inside the chlorine, bromine, and iodine. So we're going to see what happens when this reaction goes on. Okay, so reactivity decreases. So when we say reactivity decreases, right, you're going to see a difference in the what they call burning. So they burn the iron wool and then put it inside the chlorine gas. Okay, this one is the chlorine gas, and as you can see, what happens is that you will see brown color fumes coming out. All right, so technically what you are seeing here is the iron halide. Okay, so technically after they cool down, right, you will be able to see brown color solids. Okay, so doesn't matter lah, iron chloride, iron bromide, iodide, you will all get brown solid. Okay, so this one is the bromine. Okay, first they heat up the bromine, brown color gas coming up. All right, and then they are going to heat the iron wool. Okay, meaning they are going to heat up the iron right here. So they are going to wait for the iron to burn, and immediately you can see a reaction happening, and you'll see brown gas or brown fumes forming also. Okay, this one is iodine crystals. So iodine crystals, they are purple in color. So you see when they hit, right, the purple color fumes will go up. Okay, and then they are going to hit the iron wool. Now, since the reactivity is less reactive compared to chlorine and bromine, it will take a slightly longer time for the iron wool to burn. So, oops, the video stopped, right? So technically, what happens is that it will take a longer time for the iron wool to burn. Hence, you will not be able to see a very clear, what they call, burning compared to chlorine and also bromine. But you will still be able to get the brown color fume, which eventually will cool down, and then you will see brown solids. Okay, so for the reaction with the iron wool, all right, so observation is the same because reactivity decreases, right? So burns, this one we say very brightly. Okay, because as you can see from the video, they burn immediately, right? And then forms a brown solid when cooled. So this is the balance equation. All right. So for bromine, okay, they burn brightly, forms a brown solid, whereas for iron wool, they glow dimly, okay, and forms a brown solid. All right. So technically, these are the observations for the reaction between the halogen and also iron wool. Okay. So I believe that is the reaction for the halogen. Okay. So this one is the balance equation. Bromine and iron, you will get iron bromide. Okay. Iodine and iron, you get iron iodide. Alright. So here, okay, they have included the observation. So when you put the halogens into water, okay, you will see that blue litmus paper turns red, but not bleach, because this one is iodine. Whereas for bromine is bleach, or we can say decolorized, because it's getting more reactive. Okay. Okay. Hot iron, okay, glows slowly, alright, or dimly, okay. Okay, with a dull glow forms a brown solid. So technically, all three halogens will form a brown solid after cooled. Okay, just the only difference will be the called the reaction, the burning of the iron wood. Okay, so I believe that is it for the group 17 elements. Alright, so we are still left with period 3 and also a little bit on the transition elements. Okay, so see you soon. Bye.